Okay, this is November 20, paper 1, HL, and this is another implicit differentiation paper. Question, that's calculus. And the reason we see its implicit differentiation for you, what is it? Why do we see its implicit differentiation?
Because it gives us like dy dx.
It's not just that it gives us dy dx. It's something about the function that tells us that we're going to need implicit differentiation to differentiate. Your function is not defined in terms of x only.
Okay.
As soon as your function is not only defined in terms of x, then you can't differentiate with respect to x without additional techniques. So here we just want to show that dy dx, so it should be pretty straightforward. I'm going to differentiate both sides with respect to x. So y squared is going to be 2y
2y dy
dx. Now I'm going to take the derivative of sine xy, which will be cosine, and then I need to differentiate the inside function. So just to be very clear about this, so this one, 2y dy dx is equal to cosine of xy. Now what's the difference? What's the derivative of xy? What do we need to use right here?
product rule.
Good, we need the product rule. The derivative of the first times the second plus the first times the derivative of the second. So now I want to get all my dy dx's on the same side. So I transfer what I need to. 2y dy dx minus x dy dx times cosine xy is equal to cosine xy times y. Is that clear? Or did I skip a step for you?
No.
Okay. So now I'm going to factor the dy dx. It's 2y minus x cos xy equals cos xy y. And we're getting closer here to what we're being told here, right? Therefore, we have shown, as we were asked to, that dy dx equals the cosine of xy. I'll put the y in front to make it more obvious. 2y minus x cos xy. So we're satisfied with this. Second, I'm going to resize this. Okay, you had a fair point. Now I'm going to resize it more successfully, I think. Okie dokie. Put this over here. We're going to move on to B. We're going to prove that when the derivative is equal to 0, y equals plus or minus 1. So for the derivative to equal 0, what needs to be the case? Right? Our derivative was established. We just showed that this is the derivative. So what must be true?
That y cosine xy over 2y minus x cosine xy is equal to 0.
Sure. So when is this equal to 0?
I mean, I know that cosine is 0.
Well, careful. We need this to be true.
Y
When the
xy
numerator is equal to 0.
Yeah.
The denominator should not be 0. So when we finish, we might want to check that our values don't cause the denominator to be 0. So now there's two possibilities for this. There's three possibilities. Y equals 0 is one of them, but right here we're told y equals 0 is not a possibility. So this is therefore true when cosine of xy is equal to 0. Cosine of x equals, so as said differently, what's the arc cos of 0?
Pi over 2.
Okay. Do we have a domain restriction? Not explicitly.
We don't.
Okay, so pi over 2, 3 pi over 2.
3 pi over 2 plus k.
Yeah, so pi over 2 plus or minus k pi, where k
Real.
is a natural number, not a real number. We need whole numbers.
Okay.
Okay, great. We know that y can't be 0, so we have this. But that doesn't really tell me that y is going to be plus or minus 1. So now what else can we look at? Let's look at what we're told right here. Y squared is going to be sine. And this is not an obvious part. This is an HL problem towards the end. But here, if you go back to your original function, you're told that y squared is equal to sine of xy. Now check this out. We just showed that xy is equal to pi over 2 plus or minus. So therefore, y is equal to plus or minus the square root of sine of xy. What's the sine of pi over 2?
Sine of pi over 2 is 1.
It is 1. What's the sine of 3 pi over 2?
It's 1.
It's negative 1.
Oh, it's negative 1.
But this, it can't be negative 1 here, because we can't have a negative square root. So it can be pi over 2. So we're good with this. All right. So if y is going to be plus or minus, and here it can't be negative, so we just need, it should be plus 2k pi.
Yeah. But
that means that since xy, because xy is equal to pi over 2, therefore y is equal to plus or minus 1. And I think we just showed that.
Okay.
Right? At the values where this is equal to 0, cosine xy won't give 0 when xy is equal to pi over 2 plus some other values. Here, we're only going to take the values, though, but here we're going to take sine xy is going to equal, so pi over 2. I don't know if we have to mention, well, we might actually. dy dx equals 0. So we'll mention this through in part C, right? So in part C, let me minimize part B right now. Put a little indication that this is A and this is B. We're going to take the work we did in part C, and the difficult part, the non-obvious part here, is the bouncing back, I find, from the results we found here, and then going back to the original function right there, to kind of take these two things together, from your derivatives and your original function and playing them. We're finding all the coordinates for all points on C, which is the curve, where dy dx equals 0. Okay. Now, we want pi over 2. We don't want 3 pi over 2. Because if xy equals 3 pi over 2, we get the square root of a negative number. That's not good. So we're looking for pi over 2. We want xy to equal pi over 2. We don't want 3 pi over 2. We'll take 5 pi over 2. Right? Actually, that's not true.
We can have pi.
Because dy dx equals 0, we're fine. I'm sorry, dy dx will equal 0 at xy equals 3 pi over 2. So we're okay. Y is not equal to 0. But y squared, well, if it's not, we don't know what the multiple is. Okay. So I'm going to erase this. So we know that pi over 2 is a possibility. I would go 3 pi over 2, 5 pi over 2, 7 pi over 2. We want to go up to 4 pi, which is like 8 pi over 2.
Yes,
So I guess we're going to stop here.
Yep.
Okie dokie. Now, when that's the case, we want the coordinates. Well, xy is equal to that. X, therefore, equals pi over 2 y, or 3 pi over 2 y, or 5 pi over 2 divided by y. Does this make sense?
Yep, it does.
Okay. Let me erase this piece. And so once we have that, we've just established in part B that y is plus or minus 1. In our domain, though, we're just looking from 0 to 4 pi. So for all the values where x is negative, I don't really care. So I'm just going to keep y as positive. So it seems to me like these are our values. So therefore, y is always 1 or minus 1. So at y squared equals sine pi over 2 times 1 which is 1. So we're going to have 1, 1. And then 3 pi over 2, sine of, oh, sorry, it's not 1, 1. Apologies, it's pi over 2, 1. And 3 pi over 2, when y is equal to 1, y squared is equal to that. So y equals the square root of that, but that's fine. Sine of 3 pi over 2 is minus 1. Y squared would be equal to, so y would be equal to the square root of minus 1. I don't think that's possible. Does that make sense? So here we're looking for the coordinates where dy dx equals 0 on C. And C is this thing right here. So if we have at x, right, y squared is equal to sine 3 pi over 2. And if x equals y, actually at minus 1 it could work. Here, when x equals minus 1, when y equals minus 1, that's possible.
Then what is the sine of minus 3 pi over 2?
That's the same as the sine of pi over 2, which becomes back to 1. So y would equal the square root of 1, so we're okay right here. No, but that's if y was already negative 1. So I don't see that. If y was already negative 1, y squared would equal minus 1 squared equals, okay, that can work. Minus 1 squared can equal minus 3 pi over 2 this, 1, 1. That's back to 1. Oh, no, because I can't have y being simultaneously 1 and negative 1. I'm saying two things here. I'm saying that when y is equal to minus 1, y is equal to 1.
Yeah.
But that seems contradictory. So I probably can't write that. So I think I'm going to scrap this right here. I'm not going to take the values where y equals negative 1 because I end up with the square root of a negative number. Right? If y is equal to minus 1, I need to be sine of 3 pi over 2. I'm being a fool. Sine of minus 3 pi over 2 is what? It can work.
It's 1.
This is a little bit confusing. I can't quite imagine what that graph's like. We know that when dy dx, y is equal to plus or minus 1, always. Okay? So x is equal to y of 3 pi over 2 is negative. So when y is equal to minus 1, we established that y can equal to minus 1. Minus 1 squared equals sine of minus 3 pi over 2. So I guess it could work. 3 pi over 2 minus 1 can work. I take that back. Right here. Because minus 1 squared can be equal to the square root of minus 3 pi over 2, which is equal to the square root of 1. And so 1 equals 1. We're okay with that. Cool. At 5 pi over 2, here, we've gone 2, 4, we're back to here, right? So y equals 1, 1 equals 1, we're okay with that. At 7 pi over 2, y is equal to negative 1, right? We're back here, because negative 1 squared can equal negative square root of 2, which gets us back to pi over 2. So I believe these are all the coordinates on point C from 0 to 4 pi, where the derivative is equal to 0, keeping in mind that x equals plus or minus 1. That is a challenging question.